At this point, we're pretty familiar with the idea that when solving stoichiometry problems and thinking about how to plan chemical reactions in terms of the amounts or quantities of reactants to use, we really don't like living in the laboratory world of mass measurements, volume measurements, really any sort of measurement we can make of a substance. What we really want to be able to do is count molecules, and counting lives in what we've been calling mole world, where we're thinking in terms of moles, the counts of molecules. This is how they engage with each other in chemical reactions, right? Chemical equations refer to counts of molecules, not masses in grams or volumes in milliliters or things like this. Now that we've talked about molarity, we can add a key tool to our stoichiometry toolbox that allows us to go from the volume of a solution of some solute, say A, the slide here calls it A, an aqueous solution, to the moles of A in that quantity of solution. And the value here is actually enormous because most chemical reactions take place in solution. To make a chemical reaction go, molecules need to bump into each other, right? And to make that happen, we want to put molecules in phases where they're moving around. And that tends not to be the solid state or even pure liquids where the molecules are relatively not going places. In solution, solute particles are bouncing around constantly, colliding with each other regularly, and so chemical reactions are relatively fast and relatively easy. So we'll frequently use molarity when planning chemical reactions. And again, it's a bridge, moles per liter, right? It's a bridge from volume to moles or vice versa, moles to volume. And so in fact, on the other side of this diagram, we see that molarity can be used to go from, for example, the moles of a product or a different reactant to the volume of that product or reactant, or vice versa. Flowchart here is pretty abstract, but I think it'll be helpful to see how we use molarity in the context of a practice problem. And a typical situation is a problem like this. We've got a volume of an aqueous HNO3 solution reacting with an NaOH solution of known concentration. And what we ultimately want to know is the concentration of the HNO3 solution. So we're mixing two aqueous solutions, HNO3, NaOH. I know the volume of the HNO3. I know the concentration and volume of the NaOH solution, 49.22 milliliters of NaOH is required for complete reaction. And the question is, what is the molarity of the HNO3 solution? Now, if you have some experience with chemistry, you may recognize this as a titration problem. But even if you do make that recognition, for the time being, I want you to forget that and just think about this in general solution stoichiometry terms. What we're trying to do here is go from a known volume and molarity of NaOH to an unknown molarity of HNO3. And so we can develop a flowchart here like we have for stoichiometry problems where on the left we have what we know, the volume of sodium hydroxide or NaOH, and on the right we have what we want to know, which is the molarity of HNO3. And keep in mind the units here are moles of HNO3 per liter of solution. Okay, so how do we get from the volume of NaOH to the molarity of HNO3? Well, the first thing we need to do is get out of lab world and into mole world. And we'll do that by applying the molarity of the NaOH solution. We then need to go from the moles of NaOH corresponding to this volume and this molarity to the moles of HNO3. And we'll see this is relatively straightforward here because of the 1-to-1 molar ratio in which these reactants combine in this situation. Now that we have the moles of HNO3 and we also know from the problem text the volume of the HNO3 solution, we have everything we need to put those together into the molarity of HNO3, and we've done it. We have journeyed from the volume of NaOH to the molarity of HNO3. All right, what does this look like in practice? Well, now we can plug in the actual number here, 0.04922 liters. I went ahead and converted to liters since this will make it relatively easy to work with the molarity. Liters will cancel with the units of liters in the molarity. We're going to multiply by that molarity of sodium hydroxide. That will divide out these liters and leave us with the moles of NaOH. We'll use the 1-to-1 mole ratio from the balanced chemical equation, 1 HNO3 to 1 NaOH. Next, to convert, quote unquote, from moles of NaOH to moles of HNO3. And then finally, to find the molarity, well, at this point, if we calculated all this out, this would be a moles of HNO3. That number of moles was present in the original solution at a volume of 20 milliliters. So I'm just going to divide by 20 milliliters, or 0.020 liters, to arrive at the final molarity of HNO3, which, after unit cancellation, is going to end up being 0.271 moles of HNO3 per liter of solution. So in essence, what we did here was we knew the moles of one reactant, and we used stoichiometry logic to find the moles of the other reactant, HNO3, dividing by the volume of the solution that reactant was in to find its molarity in that solution. And this is an example of titration, which we'll cover in a little more detail and get some more practice in a future video, but really we'll dig into titration in much greater detail in the Chemical Principles 2 course. It should also be noted right here that you can use solution stoichiometry to find, for example, the volume of one solution needed to fully react with a volume of another solution where the concentrations are known. There again, we're doing exactly what we would with masses, just using molarity to go from volume to moles or moles to volume, the way we would use molar mass to go from mass to moles or moles to mass.